Welcome to Func Prog Sweden number 5. First, we would like to thank, as always, all our recurring viewers, and all new viewers, you're also warm welcome. Head over to the agenda for today. First, we'll have a short introduction by me, Magnus, and then we have functional programming in Python, ? Is it possible? By David Vujic. And then the second presentation is Virtual Machines for Functional Languages by Erik, Happi, Stenman. And then, in the end, I'll do a schedule and a summary. First, I would like to thank our video sponsor, Beat. Beat is a small but growing consultancy company with office in Stockholm and in Ho Chi Minh. If you want to know more about Beat, please check them out in social media or on adabeat.com. If you want to support the Func Prog Sweden community, join the MeetUp community. Follow us in the YouTube channel, on the YouTube channel Func Prog Sweden. And, of course, check out the merchandise store on funcprogsweden.myspreadshop.net, where you can buy nice t-shirts like this. If you have questions during the presentation, please use the chat to ask them, and I will read them up for the presenters. And please don't hesitate to ask questions. With that, let's get started. And our first presentation, Functional Programming in Python by David. Welcome, David, to us. Thank you. This is the second time around you're here.
Yeah.
Last time you had like Clojure script with React or Hiccup.
Yeah, that's right. Clojure script and like front-end programming.
Exactly. And now you're back with Python.
This time it's Python.
Yeah. It's more back-end.
More back-end focused this time. Yes.
Interesting.
Yeah.
Yeah. I will hand over the cable to you
so
you can get your presentation started. Voila, David.
Thank you.
Let's see if it comes up. It's always a magic thing, if it works or not.
Moment of truth.
Yeah, exactly.
What happens if I wake my computer up?
Or no?
Nothing happens.
Yay.
Oops.
It comes up. And now you have the pixel raining.
Yeah. I made that in Python. No.
This is front-end programming with the Hiccup.
Will something happen if I do something else? Should I change the resolution or something?
We'll see. We got it working just before we started.
Yeah.
As always, the demo monster is here. Welcome, David. The stage is yours.
Thank you. Okay, welcome to this talk about functional programming in Python, ? My name is David. I'm a developer. I live and work here in Stockholm, Sweden. And currently I work as a full-time Python developer. And I previously have coded in Clojure, in JavaScript, and Node.js, and C# also. And when I came back to Python not too long ago, from a functional programming language, I was thinking if it would be like possible to use some of the good stuff that I've learned from Clojure and Clojure script. So this talk is going to be a little bit about that. And I'm thinking about this. The talk could be like in three parts. The first part will be, I will talk about functions, the basics of programming, or basics of functional programming is writing functions. And also try to talk about a functional approach to data, how we can separate functions and data using functional programming in Python. And one section will be about the developer experience, about tools and workflows that will make our daily work as developers joyful. Yes. And there's something called the Zen of Python, or writing Pythonic code. If you haven't heard about it before, it's sort of it's a set of rules or guidelines on how to write Python. I think I have another, yeah, this one. So if you would like open a Python shell or a terminal and start a Python shell and import this, you would get this list called the Zen of Python. So it's sort of a Easter egg implemented in the Python shell. So here you can find like ideas on what good Pythonic code is about. And when I came back to writing full-time Python, I went back to reading this list and to see with my newly learned functional mindset if this the functional idea is applicable to these ideas, the Zen of Python. And when just quickly browsing, I thought, hey, this looks like functional to me. So I started to code and started to learn more, and I had this list in the back of my head. And after a while, I realized one thing. There's especially on line 16, where there should be one, and preferably only one obvious way to do it. But from my experience, solving a problem in Python can be done in several ways, in at least 3 ways, probably more. I'm going to show you what I mean by this. I'm going to go back to my editor, code editor. And I have a file here. And here's some code, the two functions, basically doing the same thing. So I'm starting by declaring a list of words, and what the functions are trying to do is they accept that list and trying to find a word in that list. And if it's found, it's going to return it. And the first one, I think that's a very common way of writing Python code. You take a list and you iterate through it using a for loop, and for each iteration you look at the item and compare it if it meets your requirements. If that's true, then you return the data that you have found. I think this is a very common way of writing Python. And the second function does the same thing, but I tried to write it in a more functional way or something like that. So instead of doing that for loop, I used the built-in filter function. And the filter function accepts a predicate, which do actually that matching of the requirements you have for that filter. And in Python, the filter function will return a lazy object, iterator, and to just get the first item, you can use the built-in next function. So that's 2 different ways of writing the same solution in Python. I'm going to try to write it in another way. Find word, and probably I want to try to write it in a more Pythonic way. Okay, good. Maybe that's better. So it's going to accept the same kind of input, like this. So instead of using that filter, I'm going to use something called comprehensions. Something like that. And a comprehension is a special feature in Python. And what I chose a generator comprehension, and that one also returns that iterator object that you can run the next function on. So if we quickly browse these three functions, to me it looks like the third one is sort of a combination of the first two ones. It looks like some kind of a for loop in there, but it's just a one-liner and returning that iterator. So probably, I think the third one is probably the most Pythonic of these three functions. Then I'm not sure if the comprehension is strictly functional, but I think it's a good balance between Python and functional in general to use comprehensions. And there's I used generator comprehensions, and we also have list comprehensions and dictionary comprehensions. Okay, so that was one example. Okay, so I'm going to move on to a different example, like this. So here I have a function that accepts a dictionary, some data, and add stuff to that data, and then return it. And I think this is quite a common way to writing functions where you want to like add things to an object. What I'm doing then, I'm also printing it out. So I'm going to try to actually run this function. Functions and add things. So what it does, it prints out that dictionary, and starting with the name and added hello world. So what I'm going to do next is I'm also going to print the original data source, like that, and run that function again. So first I print out the result from the function call, and then the original data. And as you can see, the both have been changed. And that shouldn't be any surprise, because I actually do things to an existing object like this. So if you would use a functional term, you could say that I mutate the data. And I think it's very common in Python because it's so easy to do it. Data in Python is mutable. It's not immutable. So you can change objects just the way you want. But mutability is mutating data. It's also something that could introduce potential risks or unwanted side effects. So we want to avoid mutations, and that can easily be done in Python too. So I'm going to, instead of adding data to that object, I'm going to use some fairly new syntax in Python. And just going to delete that row. So if we run this function again, you can see the first row there, that's the result of that function call, and the second row is the original data source. So what I'm doing here, instead of mutating the existing data source, I'm merging two dictionaries. I'm taking my original object and the new data and merge them together. Since I think Python 3.9, the pipe operator is how you can merge two dictionaries. Okay. So I'm going to move on to a little bit more of a real world example. Like this. So on my spare time, I'm working, just probably as many of you do, working on an open source project. And that thing that I've been working on is a program that works with files on a file system. And what I wanted to do, I wanted to be able to to start from a folder in my file system and look for a file, and I wanted to traverse the dictionaries or directories upwards. So looking for a file in this directory, then traverse up to next one and next one and next one. So I Googled and I found this nice and elegant function in Stack Overflow. So I just was about to start using it because I thought it was nice and simple and just a few lines of code. But then I realized what I really wanted was to be able to I wanted to be able to determine which folder which directory to start from. This function assumes that the directory that you are in currently will be where you want to start. I want to pass in that to this function instead. Then I looked a little bit closer to what's happening in this function. So it declares the current directory, and also the root, and have a sort of a guard not to traverse beyond the root folder. And then if it doesn't find the file, it's going to reset the current directory to its parent and loop until that statement above is true. So I'm thinking, what will happen if I will pass in a directory that will internally be mutated? So I wanted to avoid that, just as the example before. So I ended up in refactoring this code. Nope. Into something like this. So this function below here accepts a working directory. I still have these guards to check if I'm on the root or not, but if the file isn't found, I'm calling the function itself. So I'm using something called, a very common thing in functional programming called recursion. So instead of the current working directory, I'm sending the parent of that one. If it's not found, it's going to send that parent. So traversing upwards until I find that file, and if not found, I will return none, just like the previous function. And the result, it got a lot fewer rows, and I don't mutate any data. So this is also an example on how you can avoid mutation by doing calling the function itself, recursion. Okay. So moving on to another example. Oops. So, and as opposed to the previous one, this is totally made up. This is a totally made up example. So if you can imagine, after the pandemic, people start going back to the offices again, and but during the pandemic, it might be that your company has grown. There's a lot more people now than like 2 years ago. So we need some sort of system or app to keep track on the office itself. Is there any available desks in the office when I'm going to work there? So I started on prototyping this, and figured out that, well, we have like some sort of object, some sort of office, and the office has a number of desks. And the office is a class, and each desk is also a class. And you can ask each desk if it's free or not. And the office also has a function or a method that you can query if there are any available desks in the office. And this approach is could be seen as like an object-oriented approach to solving a problem. So if I'm going to put my functional glasses on, or having a functional approach to this, what I usually do, what I think it's quite common to do, is to identify the different parts of a problem or a program. Let's say I want to refactor this. So what I'm trying to do is to identify what is the data in this code, and what kind of calculations is done on this data. So if I can identify and separate those two things, so and I actually gave that a try. So I'm going to put this refactoring next to it, like this. So instead of the one office and a desk, I saw both of these objects as basically data, and the thing to check if an office is if a desk is free or not is a calculation on it. And what I think is quite common in functional programming, at least in languages like Clojure and equal, is that representing data is a good thing of representing data is to use just basic data types like dictionaries or lists and things like that. So I identified this office as a dictionary, and with one key called desks, and that key contains is a list of other dictionaries, which is a list of desks. And by doing this, I can send this data, just a regular dictionary, where I know like the API of what to do with that dictionary, to a generic function that can do that calculation on it. And as you can see, the code, the amount of code is a lot less than this version. And I'm probably being totally unfair to the object-oriented version here. It can be done a lot better. But I want to show you kind of a difference in the mindset of using functional versus object-oriented programming. So in functional, you would identify the different types of the different things in a program, like data, calculations, and if you would do any updates or inserts, that would be an action. So you can separate these three, and you can start writing pure, simple functions based on that thing. Okay. I'm going to turn this off a bit. I'm thinking about going back to this search function. And if you remember, I was going to my terminal and was executing some Python code. You can also start a Python shell if you want to experiment with code, and that's cool. But one thing that I have learned from mainly from Clojure is that you can use the terminal or the REPL in a much better way, which is a thing called REPL Driven Development. And I was trying to investigate if that thing was possible in other languages like Python, and I think it's you can actually do it. So what I'm going to do here is I'm going to fire up a Python shell within my editor, but I'm not going to write any code down here. What I'm going to do is that I'm going to continue working where my code lives in the editor. So capture the result, and then I can evaluate the code as I type. So I'm evaluating the result of this search upwards thing, and I can continue experimenting like this. Oh, it's found the file name is the one that I actually looked for. I can execute functions. and get the result in the terminal. So by doing this, I think this is a much smoother way to experiment and test your code than navigating back and forth between your editor and a separate shell. So I'm staying here where I have my autocomplete and like all the support. I can navigate back and forth and things like that. So that's kind of REPL driven development in Python using there's some setup you need to do in your editor. I'm using Emacs, but I'm pretty sure that this thing works in PyCharm or VS Code or whatever your favorite editor is. Okay, so that was REPL driven development. So I'm going to show you one last example of what I think is really good, a really good thing that I have learned and want to bring from the functional mindset or functional ideas into Python. And I'm going to demo. I have some example code here. So I have some code here. So I'm working on an app that takes CSV files and parses them. And this function is some sort of a validator. It validates the CSV of that file. So I'm opening in it and I'm extracting the headers and I'm looping through each header and try to do some sort of validation and return a Boolean if the CSV seems valid or not. And I think I can run this in the repo like that. Yeah, it seems to be a valid CSV. But I also have a file called empty.csv here somewhere. Let's give that one a try. Boom, my code explodes. And that's because the code here has expectations of the CSV that I hadn't thought about before. So what can be done? So, well, I thought it might be good. Maybe I need to do some, have some handling some errors in this code. So I added some error handling by wrapping parts of the code in try catch statements. So if something would go wrong when I open a file, I can handle that and return false. If the headers, if I get a key error because the data is not there, I can handle that one. I think that was actually the case before. And just to be certain, I'm going to add a try catch here, try except when I loop, because what if the headers is empty and I'm trying to iterate non-object, and then things will start to break too. So I better have a try exception there too. So, and then I grabbed a cup of coffee and came back to the computer and saw this code started to be quite a lot difficult to follow because there's a lot of exit points and things like that. So I tried to actually, well, maybe I need to do some sort of refactoring. Maybe I can extract this into separate functions. So I did that. So here's my entry point. It's nice and clean. It's sort of almost like it's piping data from the input of the output of this. It's input to next function and continuing like that. And I have kind of sort of hidden the error handling in each function like this. Try except, try except, try except. So maybe the entry point got a little bit cleaner, but it's still quite a mess. And you know, this is just example code and just one line, but I guess you can imagine real code running in production that has a couple of rows more than this simplistic example. So so what I've learned from mainly from Clojure, but I think it originates from F#, is a way to write your code using a happy path style. Because what I want to do is I want to ignore all these error handling. I just want my function to do what it's supposed to do. And one way to solve that is to use a pattern called Railway-Oriented Programming. So I've tried to implement this idea in Python. There are libraries already that you can use, but I thought it would be a fun idea to experiment and try to understand the ideas behind railway-oriented programming. So my functions ended up looking something like this instead. So I've still extracted each part into separate functions. The entry point looks basically the same. It's piping data, input, output, input, output. But the functions there, they have I've removed the error handling in the functions and instead decorated it with I've decorated the functions. And railway-oriented programming is a way to, if you have a function, you want to make the function into a two-track function. So if you run code in your function and something goes wrong, you will take the next step will be a different path, because something went wrong and you will bypass the rest of the flow, and then you can have a look in the end what was the result. Did it success or did it fail? And so I implemented that by decorating my functions like this. So if something would go wrong here, the errors will be handled, but not in this function. So if we have a look in how this works, so I'm navigating a bit into that decorator. So what's actually been handling is a try except actually. So I run my function here, and if it fails, I'm going to handle that error and return a different kind of object, a fail object. And that object contains the error information, which function failed, and anything that you like, basically. And in the next step, when that data failed object will be passed to the next function, but the decorator will make sure to check the incoming data. If it is a type of failed object, it's going to skip the flow of that function. So it's just going to return and exit that function. So in the end, what I do here is if it goes wrong somewhere in this flow, this is handled, and the result will tell me in the end if it went well or if it failed, and then I can handle that failure. And this is just I'm just scratching the surface on railway-oriented programming, but this is just a basic example on how you can write code using a happy path style and from a functional pattern into Python. And I think basically that's what I had to say today. So I've gone through, I talked about functions and avoiding mutations, how you can see data using functional mindset, and the developer experience using REPL driven development, and some patterns like railway-oriented programming. Thank you for listening. And all code is in my GitHub, so if you want to look, or please contact me if you have any questions. Thank you.
Thank you very much, David.
Thank you.
I have a request. REPL Driven Development, how did you do it with Python?
Yes.
Did you have some magic code, or can people check it up on your GitHub?
Yes, they can. I have it in a. I should have linked to my other repo. I can do that maybe in the comments, because I have a configuration for my editor describing how you can set up your editor to make this REPL driven thing work nicely.
Good. Thank you very much. Then I have next question. Have the functional type of thinking helped you when you write Python now? Has it made the code better? The Python code better?
I think so.
Yep.
I think it has helped me to isolate problems or problems to solve, and in a more like structured way. I don't nowadays I get a little bit headache when I see a function with too many too many stuff in it. So I
Yep.
want to extract and understand the problem, and for me it's easier to understand if you have like simple functions with input and output. So I think it has helped me.
Yep. Have you seen less bugs or less maintenance issues?
I don't.
Or is it too early?
It's probably too early, and I have less bugs than if I go back to the things I did like a couple of years ago, definitely. But if I don't know if the code that I have done now would be has less bug than if I would choose another approach.
Yes. Have you gotten any comments from your teammates?
Yes, I think mostly positive. I've started to introduce not this railway thing is still left to do. I'm going to try to introduce the teams to that, because we do a lot of code with many exit points and handling errors in line and things like that. So I think this approach would be fit quite nicely there, but we're not there yet.
Yes. Then again, thank you very much. I'm gonna see. Oh, no more questions in the chat. Thank you very much again, David.
Yeah, thank you for having me. Thanks.
And next presenter will be Erik, Happi Stenman. So while Erik is walking up and also getting everything set up. Yes, so while Erik is setting everything up, I will introduce Erik. He's the CTO of Happi Hacking, helping companies with software projects. Erik is one of the world's most experienced Erlang developers. He's been programming Erlang since '94. As a master student, as a doctoral student in the HYPE research group at Uppsala University. Also worked and was part of starting up, or was one of the first developers in Klarna also, in the famous CRED department. Welcome, Erik, to Func Prog Sweden.
Thank you.
Welcome. And the stage is yours.
Thanks. So I will talk about virtual machines for functional languages today. And I will start with a story from real life. So I worked at a small company. There were not 7,000 employees. There were 7 employees. And we had a service serving just a few customers. But in a few years, it grew to serving many, many customers. And then one very calm night, almost nothing was happening in the system because all our customers were basically in the same time zone, so not much happening in the night. But then suddenly one of the server nodes just disappeared. So what had happened was that this service was of course implemented in Erlang, and Erlang runs a number of schedulers, and one of them thought, well, this is such a calm night, so I'll just go to sleep, just as my son here in the picture. And since we had a machine with many schedulers and many cores, there were many schedulers, but several of them actually went to sleep because there were not much work to be done. And then there was one poor scheduler still up late at night working, and then it tried to do a built-in function in Erlang called term to binary, which takes an Erlang term and turns it into a binary representation that you can write to a log or send to the network or something like that. And it tried to do it on a 30 gig big term. So that, of course, took some time, and it was only one scheduler. And term to binary in Erlang at this time was not preemptive. I will get back to this in a while. So outside the Erlang system, there is actually another process that's called heart, that sends a heartbeat to the Erlang system and checking whether the system is live. And since there was only one scheduler running, and that scheduler was busy doing term to binary, there was no answer to the pings from heart. So then heart actually kills the system and hopes that a restart will set everything back to normal. So this is symbolized by my wife with the sword going for the kill here. So that got me more interested in actually understanding some of the deep down settings of the virtual machine of Erlang, and I started writing a book about the Beam system so that everyone coming after me now can hopefully more easily understand some of the deep down problems you can find. But today we're going to talk about two virtual machines solving two very different problems. So these different problems prompted some different language designs, and these languages in turn impacted the design of the virtual machine for the language. And we'll look a little bit into what these machines look like. So the first problem was making telephone exchanges. So this was in the early 80s at Ericsson. They realized that the majority of the development cost of a telephone exchange was actually in software. So the computer science lab at LMTEL at that time, it was Ericsson plus Telia together, set out to find out how do we want to develop software for telephone exchanges. So they saw that, well, telephone exchanges, they're always running. They have high throughput. They need to be reliable, and they need to be maintainable. So when you put a telephone exchange out in the wild, it will probably run for 20 or 30 years, or maybe even more. It turns out that these requirements came back when we started with internet and started doing web servers. So many web servers or any network service often have these requirements. So Erlang has, which is the language that was the solution to this problem, works also very well to make web services. The other problem is a little bit newer. It came with blockchains. So on blockchains after Ethereum came along, you wanted to write smart contracts. And smart contracts are neither smart nor contracts, but they are programs that you can run on the blockchain. So they're very different from an Erlang service, which is running forever. They run for a very short time. They need to be deterministic. So every time you run it on whatever hardware, wherever you run it, you need to get exactly the same result, giving the same input. And you want them to be reusable so that you can combine contracts. and they need to be easy to understand and verify, since they can handle a lot of money, real or imagined, or at least some tokens on the blockchain, which can represent money. And some banking services have similar problems, so could do with similar solutions. So as I said, the solution to the first problem was the Erlang language that was developed at the computer science lab. And the first thing that they realized in order to build a telephone exchange was that in a telephone exchange, they have at least 2 of everything in the hardware, because the hardware will break and then you want something else to take over. So you needed to be able to distribute your system and run it on more than one hardware at a time. And this led to the right concurrency model, a share nothing semantics with message passing. Also, they needed to be very easy to handle things that go wrong, and the error and exception handling in Erlang is quite robust and useful. Also, the philosophy when you write an Erlang program is very much like the Rail method that we heard, or as we say in the Erlang word, let it crash. So you usually write for the happy path and let the process crash if it goes wrong, and then you handle the unhappy path. Also, there are a couple of things that are hard when you work with concurrency. So you want to make a couple of libraries where you really think about how to do these things. And we have things like gen servers and supervisors in the Erlang libraries. Erlang also became dynamically typed, and we'll talk a little bit on some advantages with that. There's also some disadvantages, of course. And it has symbolic and transparent data structures and an interactive shell. So it's very easy to log on to a running Erlang system and actually look at what's happening in that system and understand what's happening, because everything is symbolic and everything can be seen exactly what it is. It's not just numbers in memory. Well, in the end, it's just numbers in memory, but you have things on top of it to make it easy to understand. For the other problem, writing safe contracts for a blockchain, we came up with a new language called Sophia, which is statically typed. It has no concurrency, but it's possible to run several Sophia contracts in parallel with some thoughts on how to do that, as long as they are not touching the same path of the blockchain. It has very well-defined errors, and it's safe. So, for example, there's no wrapping of integers behind the scene, like Ethereum, for example, suffer from. It has a very close integration to the blockchain that it's using. It doesn't have any floats, because you don't want floats when you're working with currency. And it has well-defined serialization of all the data and the program, so that you can get the determinism also from that. So from the first problem and the solution Erlang, after a while we got to the virtual machine Beam. So there were a number of virtual machines for Erlang in the beginning. The first ones were just emulators written in Prolog, and then there was the Jam, which was very much like Warren's abstract machine for Prolog. But then came Beam in around 98 or something like that. And Beam is a garbage collecting, reduction counting, non-preemptive, directly threaded register virtual machine. And we will look a little bit at some of those things: the garbage collection, reduction counting, and that's about it we have time for today. So I said earlier that Erlang has schedulers. So the big thing with Erlang is, of course, that it's a concurrent programming language with many processes. And on the Erlang level, all these processes are preemptive. So as a programmer, you don't really have to worry about when a process is yielding and letting some other process run. But on the Beam level, in the machine level, it's actually non-preemptive. And it uses a thing called reduction counting. So reduction is a word that comes from Prolog. And in Prolog, Prolog is trying to reduce two terms until it can find an equality or a binding that makes two terms equal. And each part of that is a reduction. Erlang kept that word and uses reductions. It's not really clear what the reduction is, but at least every function call is one reduction. So every time you enter a function, the Beam checks if you have used all the reductions that you got as a process. And if you're down to 0, then you let another process run for a while. A reduction should be something small, but as we saw with term to binary, turning a 30 gig structure into a binary representation is not really small. So, but that was quite a long time ago, and the team at Ericsson, with help from people on the outside, also have now managed to get almost all the built-in function in the Erlang runtime system to either be able to yield or both be able to yield and to count number of reductions comparable to the amount of work that they are doing. And since Erlang doesn't have any loops, the only thing you can do is to do function call and build loops by tail recursion or just ordinary recursion. Then any loop will also burn reductions by being function call. If a process wants to receive a message, then and there's no message in the mailbox that matches the message you're looking for, the process will also yield. So that's the basic of the Erlang scheduling, and you're running usually one scheduler per core or thread or pseudo core that you have in the system. So you can set this up as you want with as many schedulers or as few schedulers as you want. So if you're running several other programs on the same machine, you might want to reduce the number of schedulers that you're running in the Erlang system. So the concurrency model of Erlang is to have lightweight processes. A process has its own stack and heap. We'll look at that soon. And there's no shared memory. You can only communicate between processes with message passing, or actually through signals. And messages is a special type of signal. And there's no data that is shared, and there's also no updates. Since Erlang is a functional language, you cannot really update data. So a process cannot destroy data for another process. Erlang also has monitors and signals, so that one process can choose to monitor another process and get a signal if that process dies or killed for some reason, and can handle that. So from a high-level view, a process is just memory. It has a process control block which keeps track of, for example, the number of reductions that you have used and where in the code you're running the last function and so on. You have a stack with arguments to functions and the return address of functions. And you have a heap where you can store long-lived data. And the stack and the heap together is about 233 words when you start. And also there's a mailbox where other processes can add messages. So if we have two processes here with their memory, the stack and the heap, that are actually one memory area growing towards each other with free area in the middle. And then you have the inbox. And we have process 1 here that want to send a message, hello, to the other process. And the other process is not really waiting for the message hello, it's waiting for the message 42, at least for 1 second or 1000 milliseconds. So when this process wants to send the message, it has hello on its heap. It starts by copying it to a message buffer within its own memory area. So this it can do without disturbing any other process. And then it gives this message buffer to the other process and put it a pointer in the inbox of the other process. So this is in the general case. In some cases, and depending on your setting when you start a process, if the other process is running on the same scheduler and is not running at the time, the message can actually go directly to the heap. But in the usual case, it's just moved to the inbox. This process is not waiting for the message 42. So this receive, it will not match the hello. So it will then just keep track of the messages it has seen and waiting to hope to get the message 42. And if a new message comes in, it will just ignore the seen message box and look for new messages in the inbox. But after 1000 milliseconds, it will give up waiting for the message 42 and just receive any message. And in this case, then it will copy the message that it had in the inbox and put it on its own heap. So Erlang is dynamically but strongly typed. So you cannot do like in some language like JavaScript, add a string to an integer, or in C where everything is just data or pointers and you can basically try to do whatever you want with it. In Erlang, it's strongly typed, so if you try to add a number to a string, you get a runtime exception. But it's dynamically typed, so the compiler will not stop you from writing code that tries to add these kind of things. Of course, if it's really obvious, the compiler will warn you and say, well, this will never work because you're actually trying to add a constant string to a constant integer, and then you can have warning as errors turned on, and then this will not compile. But the nice thing with being dynamically typed is that you can actually do hot code loading. It's very hard in a statically typed language to type a program for the type that's going to be in the future. And with hot code loading, what you do is that you actually change the implementation. You can, in that way, actually change the type of a function while the program is running. And the reason often to update a program is that you might have gotten some types wrong, and you want to fix this in some place. And this would make it very hard with hot code loading, and also with having static typing of only parts of the program. You usually want the whole program to be able to do static typing. It makes it also very easy to be able to move heaps and stack, or maybe it's not the dynamically typed, but since Erlang is dynamically typed, it also has everything tagged to be able to keep track of the types. And this makes it very easy to move around heaps and stacks, and also to get the transparency of data. So you can always look into the memory and see what type all the data on the heap is. And it's making the garbage collection easy also, since everything is tagged. Erlang has a set number of types. There's no way to make any new types in Erlang. You can make abstract data types, but the built-in types is all you got. You could argue that under atom here, there is actually a subtype that is Boolean, which is the atoms true and false also, that are both Booleans and atoms. And all the types, all the values in Erlang are comparable, and they compare from left to right in this picture. So an integer is smaller than a binary, for example. So a string in Erlang is a bit special. It's one character per in a list per character in the string, needing two words on the heap, one for the character and one for the pointer to the next element in the list. So the string hello takes a number of words. This is in a 32-bit representation. In a 64-bit representation, it's obviously twice the size. I really like Erlang strings though, because you can do string concatenation in order 1, which is really hard in most languages, because Erlang strings are actually IO lists. So one time OTP, the people that making, or the organization unit that's making Erlang, decided to introduce line numbers in errors. So there's runtime errors in Erlang, and they introduced line numbers. So what could possibly go wrong? This is like perfect. It's like everything: ice cream, popcorn, bacon, brownie, and chocolate sauce. That's all you want. But it turned out that at this time we had a little loop in the program that worked by throwing an exception. So you could do a deep search and then throw an exception and not have to go back through the call stack. And just for the sake of it, the developer wrote that also did a stack trace where it caught this exception so that it could write a logging message if something went wrong. So this happened 20,000 times per second in the system, and suddenly it started to trying to find the line number for all the stack traces in this call, and that turned out to be not so efficient. Erlang has a copying generation garbage collector and just one heap per process. So there's a nice thing you can do if you know that you're going to do a calculation and then don't need all the intermediate data. You can spawn a process with a large enough heap to do the full calculation and then just let it die, and everything is reclaimed without needing to do a garbage collection. You get also a very small root set only in the stack of one process. So you get a sort of incremental garbage collection already from that. You get improved cache locality because each process has its own memory. And you can also then have the stack and heap grow toward each other, and you get a cheap test and fewer pointers. And when you do the garbage collection, you only need space for the data of one process, not for the whole system. So the extra footprint for a copying collector is smaller. On the other hand, message passing is expensive because then you need to copy the message that you're sending from one process heap to another process. And it can also use a bit more space because the stack and the heap always have this free space in between. And this is not shared between processes, but each process is using up a little bit of space. If you only had one heap, then you would have the same free space for all and reduce the fragmentation that way. So that were some highlights of the theme. So we'll take a quick look also at Fate, as it's called, the Fast Eternity Transaction Engine, which is a virtual machine built on top of Beam in order to run Sophia and smart contracts for the Eternity blockchain. So Fate has no memory limit. Instead, it's controlled by a gas price and the costs, which make it hard to try to use all the memory that you can. It has no concurrency. It's statically typed and has no floats. It has very well-defined errors and close integration to the blockchain. It's a stack-based machine, and it has a well-defined serialization. So very close to the Sophia language, also has basically the same properties, and it has Erlang's integers that can be of any size and don't wrap around, which has been a big problem for other languages. So the data types in Fate are integers, booleans, address, which is an address on the blockchain. And this blockchain also have contracts, oracles, oracle queries, channels, and all these are first-class objects, not only in the Sophia language, but also in the Fate virtual machine. It has strings and bytes, tuples, and lists, maps, and variant types. So you can also define your own types in the virtual machine. It has bits and also a type for types. So you can reason about the types in the machine. And the code is built of basic blocks. So there's no addresses or instruction addresses in the machine. It's only sequences of instructions within basic blocks. And the function has code, and code is a list of basic blocks, and the basic block is a list of instructions. So no way to jump to any place where you want in the code. You can only enter at the beginning of a basic block, and you can at the end of a basic block you can jump to different places. And there's no way to write code to memory. The code is loaded when a contract is started, and that's all that you have. The size of data is unspecified, so it's not like there's a 256-bit integer or anything like that. There's no word size. And the implementation can choose how to store the data. It's very well defined how you serialize the data, but what you do during runtime, we don't care about. So if we look at Solidity, which is a programming language for Ethereum, a identity function contract might look like the one on top here. And then we have the Sophia contract, same function, taking an integer, returning an integer. Can of course be arbitrary sized in Sophia. So if we compile the Solidity identity function to the Ethereum virtual machine, the EVM, then we get this nice bytecode. So it's full of push and pop and calls and swaps and a lot of instructions. So the Ethereum virtual machine is very low level. It's sort of based off how a CPU works more than anything else. So one of the first thing we did when we started with Eternity was to port the EVM to Eternity to the AEVM. And then we can compile the Sophia contract to the AEVM. So it's basically the same machine, slightly different programming language, which makes for slightly smaller code. But it's the same virtual machine, so it's not much that you can do there. But this is the bytecode of the Fate machine. So it's actually a functional program even on the bytecode level of the virtual machine. Of course, the words function and init and so on has representation in byte, but you can actually have this text and parse it to directly into the machine. So compared to the EVM, Fate is safer. It's typed, have structured data, arbitrary sized integers. The virtual machine is typed, so the language Solidity is also typed, but the virtual machine is not typed. But this virtual machine is also typed. And it's more efficient. So the code is on general for the AVM. If you compile the same program to the AEVM, it's almost 10 times larger. You get lower gas cost and faster execution. So to recap, the Beam and the Erlang runtime system, that's the standard implementation of Erlang. There used to be some other ones. There's not that many that hangs around anymore, and everyone is using the Beam now. Each process has its own stack and heap, and there's the Beam is the virtual machine that executes the code. Scheduling is controlled by the reduction counting. Garbage collection local to a process. It's also generational and copying. We didn't talk about that, but I mentioned copying garbage collector. And Fate the fast attorney transaction engine, a way to execute smart contracts, type safe deterministic virtual machine, and the memory is only limited by the gas that you have. It has very compact bytecode. That was what I had to talk about.
I will pop up on stage here. Thank you very much, Erik. Thank you very much. I have one question immediately. Have you written more virtual machines? Have you looked at more virtual machines, or
I might have written more virtual
yeah,
machines.
it's very interesting problem. This is like the nitty-gritty part. You know, when I did my when I studied at university, we look at VHDL code and assembler, and the last code you showed in Faith, it really looked like assembler code, like jump, you go here, you go there, like really how like the processor works.
Yes.
Yeah.
In my book, which is free on GitHub.
Yeah.
So you can just there. I actually take you through writing a virtual machine in first in Erlang and then in C for small arithmetic expressions, just to show you how easy it is to actually write a virtual machine. And I think I had some somewhere I have
that sounds very interesting
yes.
in a way.
So you can find it GitHub, Happi, the Beam book, and
yes,
there you can find some more virtual machines.
Yes, very interesting. I also have one more question. Any other computer languages people should look into, other than the main languages? You mentioned Sophia.
So Sophia is a blockchain language.
Yeah.
So it's very specific if you
into blockchain.
If you need to use that blockchain, you want to use that. Of course, there's Elixir, which is a language for Beam. Beam has other languages like Lua, and there's a Lisp for the Beam also. But yeah. I prefer the languages that you can run on the Beam.
So we understand. Also, do you use Erlang today, or are you forced to use other languages?
Both.
Both. Okay. Yes. Yes. Thank you very much. Let's see. No questions. This was a very interesting talk. Thank you very much, Erik, and thanks for coming and visiting us and sharing.
Right.
Thank you very much. With that, folks, that was like the 2 presentations tonight. Thank you very much for looking. We will be back again in like end of June with another Func Prog Sweden. And if you want to come and present, or know someone that should present, or have some work they should present, please get them to reach out to me, or please share their names and I will try to spam them and get them on here. That's it for tonight. So thank you very much, everyone, and goodbye.